Generally, silicon and germanium, they are called elemental semiconductors. So what do you mean by elemental semiconductors? All this I have discussed before. Silicon and germanium, they are called elemental semiconductors. Why they are called elemental semiconductors?
They have single elements.
Good. So, of course, they are made up of single elements. So suppose if we take silicon crystal, it is made up of silicon atoms. And if we take germanium crystal, it is made up of germanium atoms. And generally, we say that the silicon and germanium, they belong to group 4. Right? Do they belong to group 4? What do you mean by belonging to group 4? Just 1 second. Okay, students. So we said that silicon and germanium, they belong to group 4, right? So what do you mean by belonging to group 4? You're able to see this PPT, right?
Yes, ma'am.
Okay. So here in this slide, you can see I have taken silicon crystal. We know that the silicon, how many valence electrons it has? It has
Plus 4.
4 valence electrons. Okay. But are these valence electrons free? Are they free to move? The valence electrons of each silicon atom, are they free to move? Are you able to listen, ma?
Disturbance also.
ఇప్పుడు వినిపిస్తుందా?
పర్లేదు.
Okay. So what these 4 valence electrons will do? They form 4 covalent bonds with adjacent silicon atoms. I think in this figure you are able to see it, right? So as you can see, here 2 silicon atoms, they'll come together and what they'll do, they'll share their single pair of electrons. Okay, and they'll form covalent bond. And what do you mean by electrons taking part in covalent bond formation? What do you mean by electrons taking part in covalent bond formation? Yes, students.
Mutual sharing.
Yeah, of course. Once your electron is in bond formation, it's not free electron. Okay, so those electrons are nothing but electrons which are present in valence band, and we know that when electrons are in valence band, they are with no energy, they don't take part in conduction. Okay, so this is the case when your intrinsic semiconductor, it will act as insulator, and we'll assume that temperature to be 0 kelvins. So generally we'll say that at temperature 0 kelvins or under normal conditions, these silicon and germanium crystal or atoms, whatever free electrons are there, they won't take part in conduction because all of them are participating in covalent bond formation. Okay, students. But once we supply energy, what type of energy we are going to supply here? Generally, in intrinsic semiconductors, we go to high temperatures. Okay, is it clear, students? Are you able to understand?
Nice, ma'am.
Okay, so generally, what we do, we'll supply energy by going to high temperatures, and once we go to temperature above 0 kelvins, then what happens to all these covalent?
Ma'am, voice break అవుతుంది.
I hope you are able to listen now.
Yes, ma'am.
Okay. So once we go to high temperatures, what happens to these covalent bonds? Covalent bonds will break.
Break.
So what do you mean by breaking of covalent bonds? What do you mean by breaking of covalent bonds? All the story I have told you before, right? Again, we came back to. Yes. What do you mean by breaking of covalent bonds? Just look at this figure, ma. What is happening here in this figure? There is nothing but electrons which are present in the valence
Ma'am,
band.
figure కనపడట్లేదు మ్యామ్. స్లైడ్ ఇంట్రొడక్షన్ టు సెమీకండక్టర్స్ అని కనిపిస్తుంది.
కాదు ఇప్పుడు ఏం కనిపిస్తలేదు అనుకో.
ఇంట్రొడక్షన్ టు సెమీకండక్టర్స్ అని వచ్చింది మ్యామ్.
అదే వస్తుందా?
ఫస్ట్ స్లైడ్ కనిపిస్తుంది.
ఒక్క నిమిషం. వాట్ అబౌట్ నౌ?
ఇప్పుడు వస్తుంది.
Okay. So now see here. So this is the case when we have gone to high temperatures. So what exactly is happening here? Breaking of covalent bonds takes place. And what you are able to observe in this case, breaking of covalent bond is nothing but where electrons in valence band gain energy from temperature, they gain thermal energy, and they'll jump across the forbidden energy gap and they go to conduction band.
Conduction band.
Okay, so once one electron leaves valence band and goes to conduction band, there will be one process. What is that process called as? That process is generation of electron hole pair. Right, students? So what is generation of electron hole pair? It is nothing but electron in valence band. After gaining energy, it will jump across the forbidden energy gap and goes to conduction band. As a result, one hole in valence band and one free electron in conduction band are generated. So this process, it is called as generation of electron hole pair. And in order to get this, we have to go for high temperatures. So generally, this process of generation of electron hole pair takes place only if you go to high temperatures. And of course, once all these covalent bonds breaks, there are plenty of electrons taking part in conduction. So that's why this intrinsic semiconductor will act as conductor. And only in intrinsic semiconductors, we have number of electrons in conduction band equal to number of holes in valence band. Whereas if you go for other type of semiconductors like p-type and n-type, there we talk about majority and minority carriers. Okay, but in case of intrinsic semiconductors, number of holes in valence band and number of electrons in conduction band will be equal in number. Right, students?
Yes, ma'am.
Okay. Ma'am.
Yes, ma'am. Yes. Any doubts? You are able to see screen,
No, ma'am.
right? You are able to see screen.
Yes, ma'am.
So all these, I think, same story where we are talking about band having different energy levels. Then after excitation, as you can see in this figure, here valence band is completely filled with electrons. But once we supply energy, there are some electrons leaving valence band, resulting in formation of holes in valence band and free electrons in conduction band. I think we have started this process of carrier concentration also. So how we have defined carrier concentration? What exactly is this term carrier concentration?
Number of charge carriers present per unit volume.
Very good. So number of charge carriers present per unit volume of intrinsic semiconductor is nothing but carrier concentration. And what is the other name for carrier concentration? What is the other name for carrier concentration? No name, no other name. is also called charge carrier density.
Density of charge
Yes.
carriers.
So charge carrier density. So also same thing, number of charge carriers per unit volume. So other name for carrier concentration is charge carrier density. So now what we try to do, we try to find how many number of charge carriers are present per unit volume of semiconductor. Now as we said that in intrinsic semiconductor, number of electrons and holes are equal in number. So what we are going to do first, we'll try to get expression for number of free electrons in conduction band. Then we'll get expression for number of free holes in valence band, and then taking these two equations together, we'll try to get expression for total carrier concentration in intrinsic semiconductor. I think first part we have done. We have done or not? Did we get expression for electron concentration? All this we have done or not, students? Check your books.
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
I think here in place of this N of ED, I have used DN, I suppose, in the class.
Yes, ma'am.
See your books. What was the DN? DN, I said that.
Z of PD.
So instead of first finding total number of electrons in entire conduction band, what we have done, we have selected a small set of energy levels, and we are saying that let that small set of energy levels are present in energy interval D. Okay, first we'll try to find how many number of electrons are present in that small energy interval. Then after that we'll try to find total electrons in entire conduction band. Okay, and for that I think we have used this equation 1, which you are going to see now. So
Yes,
at the time I didn't use this C here. Just what is that expression we have taken? It is made up of two terms. What are those two terms? One is Z of ED, another one is
F of E.
Yes, what is Z of ED?
Density of energy
Yes.
states
Very
in
good.
an interval.
So it is density of energy states. And what is F of E?
Fermi-Dirac
Yes,
distribution.
very good. It is
Probability
called
of occupying.
Fermi-Dirac distribution function. And what does it indicate? It represents what is the probability
Probability
of
of
an energy
occupying.
level
Of electron
being
occupying an
occupied
energy
by-
level.
Yes, yes, very good.
Level.
Now we have taken this expression for density of energy states, and here we have come across one new term, ME star. What is this ME star? I think I have given you definition also. What is it called? Next students.
Effective mass of
Good. How we have defined effective mass? Check your books. I have given definition. And why only 2-3 members are answering? What about others?
When an electron moving in a
Yes.
periodic is accelerated by electric
Good,
field or magnetic
good,
field.
good, good. So when electron moving in periodic potential is accelerated by electric or magnetic field, then what happens to its mass? Mass is going to change with velocity.
varies
Well,
with velocity.
Velocity.
So that variation of mass with velocity is nothing but effective mass. Okay. So this is the expression for density of energy states, and I have told you that we have to take this equation as it is. Actually, we have to remember this equation. Okay, and then after that, we try to simplify this equation in this way. What I have done in place of E, we have replaced it by E minus EC. Why we have done this? Why we have done this? See, previous expression for density of energy states was 4 pi by h cube to ME star whole to the power of 3 by 2 e to the power of half d. Then next, in place of E, what we have done, we have taken as E minus EC. What is EC?
Change in
Bottom energy level.
EC is bottommost energy level of conduction band. And what was ED?
Top energy level of
Yes, topmost energy level of valence band. Okay. And actually my slate is not working. Otherwise, I would have done. Next class, I'll try to use digital slate. Okay, we'll try to derive it. So you can also derive it along with me. But right now, because all this we have done, just I'm revising. So here, because we are assuming EC to be bottommost energy level of conduction band, and where we have selected this energy interval D, we have selected it above EC or below EC. Students, that small energy interval we have selected in conduction band. That energy interval, it is above EC or below EC. What we have below EC? Below EC we have forbidden energy here. Above
Above
EC
EC,
we
ma'am.
have, yes, it is
Above
above
EC.
EC. So that's why in order to make sure that I am considering energy levels above EC, what I have done, I have modified expression for density of energy states as E minus EC whole to the power of half. Then next, talking about Fermi-Dirac distribution function. So what is the formula for Fermi-Dirac distribution function? 1 by 1 plus exponential E minus EF by ET. Right, students? So I think I have told you what is EF. What is EF?
EF
Again,
is
what is EF? What's the name for EF?
Fermi
Fermi
Yes,
energy
it is
level.
called Fermi energy level, and I told you that definition of Fermi energy level, it is going to be different at different temperatures, and also it is going to be different for different type of materials. And for your understanding, I think I defined Fermi energy level at one particular temperature. What is the temperature I have taken in order to explain this Fermi energy level? I have given definition. Just check your
0
notes.
Kelvin.
Yes, we
energy
have
level
selected.
which separates
Yes, at T is equal to 0 kelvins. How we have defined Fermi energy level? Yes, ma'am. At T is equal to 0 kelvins. How we have defined Fermi energy level? Yes. One second, ma'am. మీరందరు బ్యాక్గ్రౌండ్ లో పడుతున్నారంట వాళ్ళ హెచ్ఓడి ఫోన్ చేసి అదే మెసేజ్ పెట్టిండు మీ బ్యాక్గ్రౌండ్ చేంజ్ చేయండి యూట్యూబ్ లో అప్లోడ్ అవుతున్నారు సార్ ఒక దగ్గర కూర్చోలేదా సార్ శంకరయ్య సార్ మా నేను నెక్స్ట్ టైం నుంచి ల్యాబ్ లో చెప్తాను Okay, ma. So we have defined Fermi energy level as boundary energy level, which is going to separate filled energy states and unfilled energy states. Right?
yes ma'am.
Okay. So now next what we have done, we try to simplify this expression for Fermi-Dirac distribution function. We said that exponential term, it is going to be very large compared to 1. So that's why what we are doing, just for simplicity's sake, we have neglected this one. Okay. So just one second. Ma'am. So we are neglecting this 1 in the denominator. So we are left with just 1 divided by exponential e minus ef by kt. Then we know that 1 by e to the power of a, we can also write it as e to the power of minus a. So if we write it, so what is the final formula for Fermi-Dirac distribution function? Exponential ef minus e by kt. After that, what we have done, students, we have substituted this modified expressions for density of energy states and Fermi-Dirac distribution function in our previous equation 1. Are you able to see PPT?
Yes ma'am.
Okay. So after we have substituted, what we have done, we have, I think, taken out, in order to find the total number of electrons in entire conduction band, we have integrated this equation. So what are the limits of integration we have taken? What are the limits of integration?
EC to infinity. EC to
So what is the bottommost energy level of conduction band we have taken EC? And what about the topmost energy level? Because it is undefined, indeterminate, so that's why we are taking it as infinity. Okay, so after that, I think rest is integration part. Yes or not, students? So
Yes,
we
ma'am.
try to simplify this integration by assuming this e minus EC as x. I think we have done it as x, right? Here in this case, in this slide, it is epsilon. After that, I think we try to make this integral in the form of one standard integral. What is the standard integral? It is called gamma integral. And what is that form of gamma integral? Limit should be from 0 to infinity. I think in your books you have written it as x to the power of half exponential minus x by kt dx. This is what we have taken, right? And what is the value of this gamma integral? 5 to the power of half by 2 kt whole to the power of 3 by 2.
मैम ఒకసారి previous slide కి వెళ్దాం.
ఏమ్మా రాసుకోలేదా? ఒక్క నిమిషం. In class I made you do assuming it to be x, but here it is showing epsilon. Don't get confused. Right, ma?
Or
Any doubts on this derivation? So once we have substituted that gamma integral value, finally I think we got this equation. What is the final equation we got? So what is n? N represents density of electrons in conduction band. And why we are using this notation n? Why we are using this notation n for electrons? What happened? You all are there or went to sleep? Why we are using this notation n for density of electrons? No answer. See, simple logic, because electrons are negatively charged, so that's why we are using this notation n. Then what about the holes? Because holes we are treating them as positively charged. So for density of holes, what letter we'll be using? We'll be using letter P. And generally, because see, you have to remember this equation, it should be at the tip of your tongue. And it is very easy to remember this equation also, because this starting term, it will be same, more or less it will be same. And coming to this exponential term, what you have to remember here is because electrons will be present in conduction band, so obviously it will be EC. So EF minus EC by KT. What is K in the denominator? What is K? What is K here? KB.
Boltzmann constant.
Yes. What is the value of Boltzmann constant? What's the value of Boltzmann constant?
1.63 into 10 to the power of minus 23.
1.38 into 10 to the
10 to the
power
power
of
of
minus
minus
23 joule
23.
per Kelvin. Okay. So this is how we got expression for density of electrons. I think I told you to do for holes similarly, and I have written starting equations. Anyone has done it? At least tried. No one has tried. Okay, students, what I told you to do, just following in same way as we have done for electron concentration, I told you to do it for hole concentration. Okay, and what is that representation we have taken for hole concentration in small energy interval d? I think in your books you have written it as dp. Okay, again it is made up of two terms, z of e d into what I made you write here. I think we have written it as 1 minus f of e, if I am correct.
Ma'am.
Yes, ma'am.
1 minus f of e. What is 1 minus f of e? What does it indicate? What is f of e?
Electron.
F of e is probability of an electron
Electron,
occupying an
not
energy
of-
level. What
Yes,
is 1 minus f of e? Probability of an electron not occupying an energy level. That is nothing but existence of a hole. Because here we are trying to find number of holes in valence band. Okay. Then after that, I think I gave you simplified form of density of energy states and this Fermi-Dirac distribution function. I gave or not? What is that expression we have taken for density of energy states? I think in this PPT it is given as equation 3. And in place of m star you should have mh star, where mh star is effective mass of hole.
So PDE is equal to 4 pi by h cube.
Yeah. And here in place of E, what we are doing? What we are doing? We are taking it as EV minus E. What is our EV? EV is? What is EV? EV is topmost energy level of valence band. And here we are selecting energy interval above EV or below EV. Above EV we have a
Above.
hidden energy gap. No, not above, because EV is the topmost energy level. So we have to consider energy levels below EV. So that's why what we are doing, we are modifying density of energy states by replacing this E with EV minus E.
E.
Okay. Then next, I think we know what is f of e. Just now we got it. What is f of e? I think it is exponential e minus ef by kt. I think I gave you last final form. Did I give you this equation 6? I've given or not?
No, ma'am.
No.
I think on the day I have written on the board, people didn't copy. Just copy this mark. All of you write in your notes this derivation part.
Yes, ma'am.
Completed, madam.
I'm over.
This also over. I'll change slide. I hope all are writing down in your notes. Writing or not, all of you.
Yes, ma'am.
Writing, ma'am. Button, ma'am.
Yes, ma'am.
Just all of you raise your hands.
Writing,
Let
ma'am.
me see.
I'm previous slide button, ma'am. Oh, sorry.
Avalega previous slide.
Yes, ma'am.
Okay, I'm going back. Copy it fast. Now I want all participants to raise their hands. I want to know who is active and who is just. Okay, all are raising their hands. Good.